G'day viewers. In this episode we're going to talk about the Hubble tension. The Hubble tension refers to the experimentally measured difference in the rate of cosmological expansion between two completely different techniques. The first technique involves the cosmic microwave background radiation, whilst the second technique involves the observation of celestial objects. The first technique involves looking at the entire sky all at once, effectively. However, the second technique involves observing as many individual celestial objects as possible in order to measure a rate of cosmological expansion. The cosmic microwave background radiation technique yields the power spectrum Hubble constant, whilst the celestial observation technique yields the cosmic distance ladder Hubble constant. These two values of Hubble constant are different, but they should be the same. Hence, the difference between them is termed the Hubble tension and was completely unexpected. Hang on a sec. If we are saying that the Hubble tension is real, where is the myth? Why does the title of this episode claim that the Hubble tension is a myth? Well, the myth is that the existence of the Hubble tension is unexpected. The standard model of cosmology has been surprised by the existence of the Hubble tension. However, we are saying that the Hubble tension is to be expected, not unexpected. This means that the standard model of cosmology is not broken. All is good and everything fits into place. We will launch into a detailed explanation shortly, but for the moment, I would like you to consider the following. Right now, as far as science is concerned, the standard model of cosmology is potentially broken. This means that quite a few astrophysicists and cosmologists around the world are obtaining grants, making money and advancing their careers by trying to solve the Hubble tension problem. Quite clearly, because of financial motivation, bias is present in the scientific community. Who on earth wants to claim that a problem doesn't exist when claiming one does exist is so profitable? At the end of the day, like so many things in life, everything boils down to money. Therefore, in this video, I'm asking viewers to make a choice. That is, what makes more sense generally speaking? Taking a position which does not break the standard model of cosmology, or taking a position which does break the standard model of cosmology? Which one of these two choices is more likely to be the correct one? Obviously, an explanation which supports the existing standard model of cosmology is more likely to be the correct explanation, rather than claiming that the sky is falling and the standard model of cosmology needs to be rewritten. Yes, rewritten, because the Hubble tension is showing us that the rate of cosmological expansion of space-time is not uniform, it is variable. Hence, a key assumption within the standard model of cosmology requires a complete rewrite. That is, various regions of space-time are expanding at different rates. Given what I've just said, it seems that I'm saying on one hand that the standard model of cosmology is not broken, but on the other hand, I'm saying that it is broken. On one hand, I'm saying that the standard model of cosmology is not broken because the Hubble tension is to be expected, but on the other hand, I'm saying that the standard model of cosmology is broken because the Hubble tension demonstrates that various regions of space-time are expanding at different rates. So then, how is it possible for the standard model of cosmology to be broken and unbroken at the same time? How can we avoid this apparently circular logic? Well, the answer is obvious. It cannot be broken and unbroken simultaneously. The bottom line is that the standard model of cosmology is not broken, and now I'm going to show you how and why this is the case, whilst allowing for various regions of space-time to expand at different rates. The way I'm going to do this is by using the same equation to calculate both forms of Hubble constant. Now, that's a very important statement I just made, so I will repeat it. I'm going to use one equation to calculate both forms of Hubble constant. The fact that I'm using a single equation to calculate both forms of Hubble constant is an extremely powerful statement. If both forms of Hubble constant were so utterly disconnected, as experimental observations statistically demonstrate, then two equations should be required, not just one. Thus, as I mentioned a moment ago, the fact that I'm using a single equation to calculate both forms of Hubble constant is an extremely powerful statement. My sincerest apologies for hammering you about this, but I could not think of another way to emphasise my point strongly enough so that you keep it in mind at all times. As a consequence of everything I'm saying, I'm going to show you that the Hubble tension reduces to zero if we observe enough celestial objects, and more importantly, I will show you how and why the Hubble tension manifests itself to begin with. In addition to this, you will see how the Dark Energy Spectroscopic Instrument, that's DESI, collaboration, experimentally validates our hypothesis that the so-called Hubble tension is fictitious and doesn't actually exist, based upon DESI-2024 Data Release 1. You'll see this in the last couple of slides, so please stick around to the end of this video presentation. Please remember that when I claim that the Hubble tension does not exist, what I mean is that the Hubble tension is to be expected, not unexpected, as the standard model of cosmology insists. The DESI collaboration consists of hundreds of scientists. Utilising a new technique, they have determined that the Hubble constant as measured via the expansion of giant cosmic bubbles is 68.52 kilometres per second per megaparsec. This yields a similarity to our average value of cosmic distance ladder Hubble constant of 99.78%. What is important to note about this similarity is that the DESI collaboration is observing more than 1 million galaxies every month. However, we were able to achieve an almost identical result from only 10 galaxies. Therefore, it is quite clear that the correlation between the DESI collaboration results and our results can only be described as astonishing. Moreover, when the DESI collaboration also considers the influence of the cosmic microwave background radiation, they determine the value of the Hubble constant to be 67.97 kilometres per second per megaparsec. This yields a similarity to our average value of cosmic distance ladder Hubble constant of 98.98%. Once again, the correlation to our results can only be described as astonishing. Therefore, based upon DESI collaboration experimental results, we may reasonably conclude that our hypothesis that the so-called Hubble tension is fictitious has been experimentally verified. That is to say, the so-called Hubble tension is to be expected, not unexpected, as the standard model of cosmology insists. Hence, the DESI collaboration has experimentally proven that the so-called Hubble tension is a myth. Okay, that's enough melodramatics from me. Let's get into it. One of the most important numbers in our understanding of the universe is the present value of the Hubble constant. Cosmology relies upon the Hubble constant to tell us how big the observable universe actually is via the measurement of its rate of expansion. The typical unit of measure for the Hubble constant is kilometre per second per megaparsec, that is, the velocity of expansion per very large distance. The Hubble constant is termed constant because it is assumed that it does not vary over distance. However, it is expected to have varied over time. We should emphasise in the strongest possible language that the Hubble constant actually being constant across distances is an extremely significant assumption made by the broader scientific community, which is not based in any scientific fact whatsoever. It is a predominantly uncontested and automatically accepted position that the Hubble constant is spatially constant and that all points in space are moving apart at the same rate. In this episode, we shall challenge this position, demonstrating that the so-called Hubble tension does not exist. By this we mean that the Hubble tension is to be expected, not unexpected. Hence, the so-called Hubble tension is actually a myth. Okay, let's take a closer look at the experimental observations behind this so-called Hubble tension. The Hubble tension refers to the disagreement in results between the two key methods for measuring the value of the Hubble constant. The oldest method is termed the cosmic distance ladder method and involves converting the brightness of objects in the night sky into a value for the Hubble constant. In 2001, it was measured to be approximately 72 kilometres per second per megaparsec, and then measured again many years later as 70 kilometres per second per megaparsec. The measurement at 72 involved a type of star called Cepheids, whilst the measurement at 70 involved a type of star called red giants. However, the difference between these two measurements isn't really the problem. The problem arrived in 2013 when the second method, termed the Cosmic Microwave Background Radiation Power Spectrum method, measured a value of 67 km per second per megaparsec. The second method involved utilising satellites to measure very small fluctuations in the temperature of space-time and converting it into a value for the Hubble constant. But how can space-time have a temperature? Well, it has a temperature because microwaves are moving through space-time in every direction which are left over from the Big Bang. These microwaves have a specific wavelength we can measure, and this wavelength can be converted to a value of temperature, just like black-body radiation. As already mentioned, these very small fluctuations in space-time temperature are converted to a value for the Hubble constant, but this power spectrum value is statistically different enough from the stellar values for a problem to exist. This problem is termed the Hubble tension. On the next slide, we shall show you how we derive the experimentally confirmed Hubble constant for Cepheids, red giants and the Big Bang. In doing so, we utilise a single equation, thereby demonstrating that the so-called Hubble tension is to be expected, not unexpected. In other words, the so-called Hubble tension may have been a surprise to the entire astrophysics community, but it was not a surprise to us. Okay, let's take a look at the math. This is a summary slide taken from episode 10. If you have not watched episode 10, now would be a good time to pause this video and review it. The journey through episode 10 is arduous, so you may need to watch it several times. However, the rewards are well worth the effort. Let's begin by loading and describing each slide component. The first tranche of information we have loaded contains episode 10 achievements. The DESI-2024 Power Spectrum Hubble Constant published in Advances in Astronomy, the PDG-2022 Power Spectrum Hubble Constant, the PDG-2022 Solar Distance to Galactic Centre, and an estimate for the total mass of the Milky Way galaxy, which we have assumed is equal to its virial mass. It should not escape your attention that the DESI-2020 and PDG-2022 Power Spectrum Hubble Constant values are experimentally verified and virtually identical. The second tranche of information to load is the mathematical solution which produces the cosmic distance ladder Hubble constant and the cosmic microwave background radiation power spectrum Hubble constant. On the right hand side of the screen you see the cosmological expansion function, which contains two configurations, the astronomical configuration and the cosmological configuration. The cosmological expansion function mathematically models the actual cosmological expansion process, whilst the present epoch Hubble constant appearing on the left-hand side of the screen calculates the value of the Hubble constant at the end of the cosmological expansion process, that is, the present-day values of Hubble constant which we measure. As you can see from the process arrow, the cosmological expansion function feeds into the present epoch Hubble constant. The two cosmological expansion function configurations shown are in fact formulated from this same equation, with slightly different inputs. The differences in inputs have been highlighted by the purple bars appearing on screen. The third tranche of information to load is a set of exact analytical solutions to a mathematical constant appearing as St sub k. St sub k represents an experimental relationship function which has various forms. In its k sub lambda form, St sub k represents an experimentally implicit Planck scale. Please refer to the summary slide in episode 6 for more information. However, in its lambda sub x form, St sub k represents the experimentally implicit Planck scaling factor associated with the size of the Big Bang singularity. Or in other words, in its lambda sub x form, St sub k is associated with the size of the universe at an instant prior to the Big Bang. Please refer to episode 9 for the complete derivation of lambda sub x. Notably, when St sub k equals 1, the historical representation of the Planck scale is applied without any form of reinterpretation or experimentally implicit scaling factor. The fourth tranche of information to load are our results for the cosmic distance ladder Hubble constant. As you can see, by injecting various values of St sub k and recalling that St sub k represents an experimental relationship function, we are able to generate the cosmic distance ladder Hubble constant associated with red giants and Cepheids. Please keep in mind that our St sub k values are forwardly derived exact analytical solutions. They are not fudge factors introduced in order to make everything work. The fifth tranche of information to load are our results for the cosmic microwave background radiation power spectrum Hubble constant. As you can see, our results align extremely well with STORTY 2020 and PDG 2022. The key achievements shown on this slide are threefold. Number one, the derivation of the experimentally verified cosmic distance ladder Hubble constant, that is, the astronomical Hubble constant. Number two, utilising the same equation, we derived the experimentally verified cosmic microwave background radiation power spectrum Hubble constant, that is, the cosmological Hubble constant. And number three, very importantly, we have eliminated the Hubble tension problem by producing both sets of experimentally verified results from a single equation. In other words, from our perspective, the so-called Hubble tension does not exist because the difference between the astronomical and cosmological Hubble constants has been predicted and experimentally verified. Let's now have a quick look at the influence of the solar distance to galactic centre and Milky Way mass. Based upon the impressive experimentally verified results we obtained on the previous slide, some viewers may be speculating that our mathematical model is highly susceptible to key inputs, that is, the solar distance to galactic centre and Milky Way mass. However, by inspection of the results appearing on screen, we can see that the influence of the changes in solar distance to galactic centre as published by the particle data group are trivial and may be disregarded. Moreover, once again, by inspection of the results appearing on screen, we see that the influence of significant variations in Milky Way mass estimates are also negligible. In fact, we can see in the middle of the slide, contained within the blue box, that if the Milky Way mass is halved or doubled, the impact to the astronomical Hubble constant is trivial and therefore may also be disregarded. So then, what's the bottom line? What are we showing via the results presented on this slide? Well, the bottom line is that the mathematical model we constructed in episode 10 is extremely robust with respect to solar distance to galactic centre and Milky Way mass. In fact, we demonstrated on the previous slide that our exact analytical solutions to St sub k are significantly more important than the solar distance to galactic centre and or Milky Way mass. Now is a good time to remind viewers that St sub k represents an experimental relationship function which has various forms. In its k sub lambda form, St sub k represents an experimentally implicit Planck scale. However, in its lambda sub x form, St sub k represents the experimentally implicit Planck scaling factor associated with the size of the Big Bang singularity. Or in other words, in its lambda sub x form, St sub k is associated with the size of the universe at an instant prior to the Big Bang. Notably, when St sub k equals 1, the historical representation of the Planck scale is applied without any form of reinterpretation or experimentally implicit scaling factor. Let's now pull together what episode 10 has shown us. Episode 10 provides preliminary evidence that the so-called Hubble tension does not actually exist. That is to say, it does not exist because it is to be expected, not unexpected as the standard model of cosmology insists. Moreover, the fact that we are able to generate the astronomical and cosmological Hubble constants from a single equation is strong evidence that the so-called Hubble tension is fictitious. Thus, the correlation of our results to experimental verification is astonishing and should not be dismissed. The primary tools utilised to achieve this outcome has been Buckingham pi theory and dimensional analysis techniques. For viewers unfamiliar with these standard engineering tools, we recommend that you undertake the appropriate course of study. Moreover, for viewers wishing to consult literature relevant to episode 10, you may do so by accessing the links shown. Okay, so now that we have compiled evidence in episode 10 demonstrating that the Hubble tension does not actually exist, is there any additional evidence to support this contention? Yes, there is, and we can find it in episode 12. In episode 12, we derived a cosmic microwave background radiation constrained estimate for the mass of the Milky Way. In doing so, we showed that DESI-2024 ED-2021, Karukas 2020 and Watkins 2019 Milky Way mass estimates may be discarded. Their results are not cosmic microwave background radiation temperature constrained, therefore they are in tension with the cosmic microwave background radiation power spectrum Hubble constant. Moreover, we also calculated the ideal virial mass limits for the Milky Way, constrained by cosmic microwave background radiation temperature limits. In addition to this, we resolve the Hubble tension and prove that it does not exist by demonstrating that the cosmic microwave background radiation power spectrum Hubble constant and the cosmic distance ladder Hubble constant may be determined utilising a single equation. Very importantly, we showed that cosmic distance ladder measurements of the Hubble constant need to consider the mass of the host galaxy and the distance of the celestial object being studied, example Cepheids and/or red giants, to their galactic centre. We will look at the distance to galactic centre consideration a bit later on, graphically, but next we will show you where you can find a step-by-step scientific publication formally demonstrating that the so-called Hubble tension does not exist. That is to say, it does not exist because it is to be expected, not unexpected, as the standard model of cosmology insists. At this juncture, we recommend finding time to review episode 10 and 12. However, if your preference is for a formal step-by-step scientific research article, you can access it via link number 1 appearing on screen. To cut a long story short, we are going to outline how the so-called Hubble tension can be disproven in 5 steps, as follows. Step 1 involves a research article published by the Australian Institute of Physics in 2008. In 2008, Storti predicted a cosmic microwave background radiation power spectrum Hubble constant of 67.1 km per second per megaparsec. However, in 2008, the Particle Data Group published a value of cosmic distance ladder Hubble constant as being 73 km per second per megaparsec. It is important to know that in 2008, the Particle Data Group was unaware of the existence of the cosmic microwave background radiation power spectrum Hubble constant. As far as the Particle Data Group were concerned, only the cosmic distance ladder Hubble constant could exist. In 2013, the Planck satellite was launched and the cosmic microwave background radiation power spectrum Hubble constant was revealed to science. Importantly, in 2013, the Particle Data Group abandoned their cosmic distance ladder Hubble constant value of 73 km per second per megaparsec in favour of the cosmic microwave background radiation power spectrum Hubble constant as measured by the Planck satellite, which was 67.3 km per second per megaparsec. The impressive fact to note is that the Particle Data Group 2013 value of 67.3 km per second per megaparsec aligns perfectly with the Storti 2008 value of 67.1 km per second per megaparsec. In other words, Storti predicted the cosmic microwave background radiation power spectrum Hubble constant 5 years in advance of experimental confirmation via the Planck satellite, as published by the Particle Data Group. Step 2. We take the experimentally verified success of step 1 and we replicate the process, but this time we apply it to a spectrum of other authors in order to assess their results. When we do this, we find that their Milky Way mass estimates align well, generally speaking, with the cosmic microwave background radiation power spectrum Hubble constant. Step 3. We summarise the quantitative results from step 2 into an easy-to-comprehend qualitative representation. However, when we constrain estimates specifically to the cosmic microwave background radiation temperature, we see that the only author who published Milky Way mass estimates satisfying cosmic microwave background radiation temperature constraints is ED-2017. Hence, as stated previously, we can see that, generally speaking, Milky Way mass estimates align well with the cosmic microwave background radiation power spectrum Hubble constant. The function of these first 3 steps is to establish a quantitative and qualitative relationship between astrophysics and cosmology. Establishing this connection is essential because we shall use it going forward in order to demonstrate that the so-called Hubble tension diminishes to 0 when the population of cosmic distance ladder observations tends to infinity. In other words, we shall demonstrate that the scientific disciplines of astrophysics and cosmology converge when the number of astronomical observations tends to infinity. Okay, let's now look at steps 4 and 5. Step 4 involves converting apparent galactic mass estimates into virial mass estimates which are constrained by cosmic microwave background radiation temperature. We considered 10 galaxies in our analysis, and you can see by inspection of Table 7 that the virial mass estimates calculated support the apparent galactic mass estimates extremely well. This is an important development because the similarity of our virial mass estimates to the apparent galactic mass estimates which have been compiled by others independently implies that the process we have executed is valid. In other words, significant dissimilarity between apparent galactic mass estimates and virial mass estimates would imply that some sort of mathematical modelling error has occurred. However, this is clearly not the case. Both sets of estimates align extremely well with each other. Step 5 builds upon Step 4 by combining virial mass estimates with apparent galactic radius estimates from Table 7. Hence, we are able to calculate the cosmic distance ladder Hubble constant as appears in Table 9. You can see in Table 9, as emphasised, that the average value of the cosmic distance ladder Hubble constant tends to the cosmic microwave background radiation power spectrum Hubble constant as the number of galactic observations tends to infinity. In other words, the so-called Hubble tension diminishes to zero as the number of appropriate stellar observations at the apparent galactic radius tends to infinity. A prime candidate for study is galaxy M82, as emphasised on Table 9. Okay, now that we have quantified the manner in which the so-called Hubble tension diminishes to zero, let's visualise how this physically may be occurring. The so-called Hubble tension arises via the apparent difference between the Hubble constant when measured utilising cosmic distance ladder techniques and the value obtained when utilising the cosmic microwave background radiation, also known as the power spectrum Hubble constant. So then, how can these values be significantly different when they are meant to be measuring the same thing? The Hubble constant is a measure of the rate at which space-time is expanding. However, the fundamental assumption made within the standard model of cosmology is that space-time is expanding uniformly in all directions. In other words, the Hubble constant is indisputably spatially constant. When one pauses momentarily to consider this assumption, one is left with the extremely obvious conclusion that there is no experimental evidence for the existence of this basic assumption. In fact, this assumption has now become scientific religion. Appearing on screen, you will see a population of galaxies. When we observe a specific celestial object tethered to a galaxy, we measure a certain value of Hubble constant, appearing as H0. We term this as being the astronomical Hubble constant, and it forms the basis of the cosmic distance ladder measurement technique. However, when we observe the cosmic microwave background radiation, we measure the power spectrum Hubble constant. We term this to be the cosmological Hubble constant. At this stage, I will emphasise that this video presentation is a companion publication to the article appearing in the link at the bottom of the screen. Okay, now that we have defined what the problem is, let's explain why the difference in Hubble constant measurements is fictitious and doesn't actually exist. In other words, let's explain why the so-called Hubble tension is to be expected, not unexpected as the standard model of cosmology insists. Therefore, the standard model of cosmology is perfectly fine, nothing is broken, and nothing requires fixing. To begin explaining the cause of the so-called Hubble tension, we will borrow a concept from sonic black holes and the famed Canadian physicist William George Unruh. A lot of public information exists dealing with sonic black holes and Unruh's work, so we'll leave this up to yourself to investigate. However, to cut a long story short, we shall be treating space-time like a fluid in motion. Moreover, rather than space-time flowing into a black hole, we'll consider space-time to be a fluid flowing towards the centre of mass of a galaxy. This means that space-time will appear to be flowing faster the closer an observational target gets to the centre of mass of a galaxy. When we add the effects of accelerated cosmological expansion as a consequence of the Big Bang, we end up with a value of cosmic distance ladder Hubble constant appearing as H0, which is higher than the value of the power spectrum Hubble constant appearing as H5. Thus, the difference between H0 and H5 is termed the Hubble tension. If you are observant enough, you may have noticed that we started this slide with a blank sheet of paper. This represents our toy universe, which is known as a bare vacuum. That is, nothing exists, not even the quantum vacuum. We then added a straight blue line which denotes the ground state of the quantum vacuum, termed the zero-point field. The zero-point field may be envisioned as raindrops on the surface of a pond. Each ripple represents the creation-annihilation process of a virtual particle pair. This process experimentally manifests as the Casimir effect, and we believe it to be the driving effect underpinning accelerated cosmological expansion. Consequently, we measure the power spectrum Hubble constant appearing as h phi. Then we added a galaxy in plan view, along with an observation target. This could be a red giant or Cepheid or something else which produces light and is suitable. It doesn't actually matter what it is, only that we can observe it and execute the appropriate measurements. From this object, we obtain the cosmic distance ladder Hubble constant appearing on screen as h0. Hence, the so-called Hubble tension has arisen. Next, we project the galaxy onto the zero-point field in the manner shown, such that it generates a space-time drain into which space-time can flow, ending up in what we term the dark reservoir of quantum potential energy. It should be noted that volumetric projection onto a two-dimensional plane is a common engineering technique heavily utilised in fluid mechanics, particularly involving aerodynamics and aerospace engineering. Finally, as we can see, the dark reservoir of quantum potential energy is the energy source powering the zero-point field and consequently the Casimir effect and accelerated cosmological expansion. Hence, the obvious question now is, what about dark energy? Where does it sit in all this? Well, in the context of this specific illustration, dark energy is represented by the sum of effects contained within the brown box, as shown. Let's now summarise what we have learned. The concept of the so-called Hubble tension, which is the apparent difference in the Hubble constant measured using cosmic distance ladder techniques and the cosmic microwave background radiation, is explained in the context of the assumption of uniform space-time expansion in all directions. Our presentation proposes that space-time may be treated as a fluid flowing towards the centre of mass of a galaxy, influenced by concepts from sonic black holes and physicist William George Unruh. The accelerated cosmological expansion resulting from the Big Bang and the flow of space-time towards the centre of galaxies contributes to the observed so-called Hubble tension. The difference between the Hubble constants is a consequence of space-time behaving like a fluid, and ultimately there is no actual tension, thus asserting the validity of the standard model of cosmology. In other words, the standard model of cosmology is fine, nothing is broken, and nothing needs to be fixed. Lastly, please remember that episode 72 is a companion document to the research article appearing in the link at the bottom of the screen. Let's now take a quick look at cosmic bubbles. An article appearing in Science Alert titled "Giant Cosmic Bubbles Have Given a New Precision Measurement of Expanding Spacetime," written by Michelle Starr, references a scientific publication based upon the first year of data collected by the Dark Energy Spectroscopic Instrument, that is, DESI Data Release 1. The research effort is called the DESI Collaboration and consists of hundreds of scientists. Utilising a new technique, they have determined that the Hubble constant as measured via the expansion of giant cosmic bubbles is 68.52 kilometres per second per megaparsec. This yields a similarity to our average value of cosmic distance ladder Hubble constant of 99.78%. What is important to note about this similarity is that the DESI collaboration is observing more than 1 million galaxies every month. However, we were able to achieve an almost identical result from only 10 galaxies. Therefore, it is quite clear that the correlation between the DESI collaboration results and our results can only be described as astonishing. Moreover, when the DESI collaboration also considers the influence of the cosmic microwave background radiation, they determine the value of the Hubble constant to be 67.97 kilometres per second per megaparsec. This yields a similarity to our average value of cosmic distance ladder Hubble constant of 98.98%. Once again, the correlation to our results can only be described as astonishing. Let's now summarise what we have learned. Based upon DESI collaboration experimental results, we may reasonably conclude that our hypothesis that the so-called Hubble tension is fictitious has been experimentally verified. That is to say, the so-called Hubble tension is to be expected, not unexpected as the standard model of cosmology insists. Hence, the DESI collaboration has experimentally proven that the so-called Hubble tension is a myth, as we claimed in our introduction.